We now start the fourth module of chapter 3, and we will be introducing the notion of rank of a matrix. We will be using the concept of linear transformation to define rank of a matrix, and then we will revisit the system of linear equations. We will see that we can give solvability criteria using the notion of rank. Let M and F denote the set of all M cross N matrices with entries from a field F. We have seen this before. This itself is a vector space over a field. This is nothing but the collection of all M cross N matrices, and if M is equal to N, then it is the collection of all square matrices with entries from the field F, and that is denoted by MNF. A definition: let A be an M cross N matrix over F. We define a map denoted by L suffix A, and the map is from Fn to Fm. The map is defined as La of x is equal to A dot x, where x is this vector x1, x2, xn in Fn. We have seen before that elements of Fn have been written in the column form rather than row form, and you can see that the definition A dot x makes sense because A is an M cross N matrix and x is an N cross 1 matrix. Therefore, this multiplication is meaningful and it produces another M cross 1 column matrix, that is an element of Fm. So, it is a very easy verification that La is a linear transformation from Fn to Fm over F, and this is what we call the left multiplication transformation. So, given a matrix A, M cross N matrix over a field F, we can naturally define a linear transformation La from Fn to Fm, and we use this transformation to define rank of the matrix A, and the definition is it is dimension of the range of La, that is rank of the linear transformation La. This is a finite number because La is a linear transformation from Fn to Fm, and therefore range of La is going to be a subspace of Fm and a finite dimensional subspace. Therefore, dimension is going to be a finite number. In fact, it is less than or equal to m. So, this is how we define rank of a matrix. Some simple observation: if A and B are two M cross N matrices over a field F, then La is equal to Lb if and only if A is equal to B. This follows from the definition of the linear transformation, because La of x is Ax and Lb of x is Bx. So, if A is equal to B, then Ax is equal to Bx for all x in Fn, and conversely, if Ax is equal to Bx for all x in Fn, then in particular Aei is equal to Bei for every canonical basis vector Ei, and therefore A must be equal to B. And the second part of the proposition says that the matrix representation of La with respect to the basis B and B dash is nothing but the matrix A, where B and B dash are the canonical basis for the vector spaces Fn and Fm respectively. Well, this is also fairly obvious because of the definition of La. La of x is Ax, Therefore, LA of EI is AEI, but we know that AEI is nothing but the ith column of A, and therefore the matrix representation of LA with respect to the standard basis has to be the matrix A itself. And the next proposition says that if V and W are two finite dimensional vector spaces over the field F with ordered bases B1 and B2 respectively, if T from V to W is a linear transformation, then rank of the linear transformation T is the same as the rank of the matrix box T B1 B2, that is the matrix representation of the linear transformation T with respect to the chosen basis B1 B2. So, this also follows from the definition of rank. We now prove a theorem. Let A be an n cross n matrix over the field F, then the following statements are equivalent. Statement 1, A is an invertible matrix. Statement 2, LA is an isomorphism, and statement 3, rank of A is equal to n. We prove in the following fashion. We first show that statement 1 implies statement 2, then we show that statement 2 implies statement 1. This would prove that statements 1 and 2 are equivalent, and finally we've proved that statement 2 and statement 3 are equivalent. So, proof of 1 implies 2. Suppose that A is an invertible matrix, then we know that A inverse exists as an n cross n matrix such that A dot A inverse is IN. IN is the n cross n identity matrix. Therefore, in the level of transformations, we can write that the identity operator on Fn, which is LIN, and that is LA A inverse, that is because A inverse is IN, and it is easy to verify from the definition of LA that LA A inverse is nothing but the composition of LA and LA inverse, where LA appears on the left hand side and LA inverse appears on the right hand side. And similarly, if we consider A inverse dot A is IN and do the same thing, then we obtain LA inverse composition LA is identity on Fn. Therefore, we have proved that LA is an isomorphism and the inverse operator of LA is LA inverse. Now, we prove 2 implies 1. So, suppose that LA is an isomorphism, then there exists a linear operator T from Fn to Fn such that T circle LA is LA circle T is identity operator on Fn. Let B denote the matrix representation of the linear operator T with respect to the standard basis B of Fn. Then LB is T, and it follows that B is nothing but A inverse. Well, that can be seen easily because T is LB and therefore LB circle LA is LA circle LB is equal to identity of Fn, and therefore L of A composition B and L of B composition A, they match, and that is L of the identity matrix, and therefore A circle B is equal to B circle A is equal to IN, which shows that B must be equal to A inverse. And finally 2 if and only if 3. So, if LA is an isomorphism, if and only if LA is onto, that is surjective, if and only if dimension of the range of LA is equal to n, and if and only if rank of A is equal to n, because dimension of range of LA is nothing but rank of A. Therefore, we have proved that LA is an isomorphism if and only if rank of A is equal to n. A technical but a very useful result. Let A be an M cross n matrix over F. Let P and Q be invertible M cross M and N cross N matrices respectively with entries from F. Then rank of AQ is equal to rank of A, rank of PA is equal to rank of A, and rank of PAQ is equal to rank of A. In other words, if we take the matrix A and multiply it by an invertible matrix from the right hand side or from the left hand side or from both sides, then rank does not change. To prove this theorem, again we go to the level of linear transformation. So, the first statement, look at the range of LAQ, but we know that LAQ is LA composition LQ. Therefore, range of LAQ is range of LA composition LQ, but we know that Q is an invertible matrix. Therefore, LQ is an isomorphism, and therefore range of LQ must be the whole of Fn. Therefore, range of LA composition LQ is equal to range of LA, and this proves that rank of AQ must be the same as rank of A. Now, the proof of statement 2, both range of LA and range of LPA are subspaces of Fm, and we know that LPA is LP composition LA, where LP is an isomorphism because P is an invertible matrix. Therefore, dimension of range of LA is the same as dimension of range of LPA, and therefore rank of PA is equal to rank of A. And part 3 follows from 1 and 2 because rank of PAQ is the same as rank of PA, that is by part 1, and that is the same as rank of A by part 2. We know that elementary row operations and elementary column operations on a matrix amount to pre and post multiplication by elementary matrices. This we have seen before. Therefore, as a corollary to the previous theorem, we get elementary row and column operations on a matrix preserve rank. This is really useful because we know that we can transform any matrix into its row reduced echelon form by applying finite number of elementary row operations. And what this corollary says is that the rank of a matrix is the same as the rank of its row reduced echelon form. And what is interesting is that the rank of a row reduced echelon form is nothing but the number of non-zero rows in the echelon form. Therefore, the rank of a matrix is equal to the number of non-zero rows in a row reduced echelon form of the matrix. But here we can ask a question which is really pertinent, and the question is, Is row reduced echelon form of a matrix unique? We define rank of a matrix as the rank of the linear transformation LA. Now the question is, how does one compute the rank of a matrix? Because rank of a linear transformation means it is the dimension of the range of the linear map, and we surely have a bound, but it may not be that easy to compute the dimension of a subspace. But when we introduced the elementary row operations, then we saw that rank of a matrix is the same as the rank of its row reduced echelon form. This gives us a method to compute the rank of a matrix, provided of course we know that row reduced echelon form is unique. We now prove a theorem which talks about the structure of a matrix, and we will see that it will have very useful corollaries. The theorem says that if A is an m cross n matrix of rank R, then R is at most minimum of m and n. And by an application of a finite number of elementary row and column operations, A can be put into the form D, where D is written in the block form. So what you see on the top left corner is IR, that is the R cross R identity matrix, and 3 spots filled with the 0 matrices. So in other words, there exist invertible matrices B and C of sizes m cross m and n cross n respectively, such that BAC is equal to D. D is that above matrix, and the matrices B and C are nothing but products of elementary matrices. Well, you can understand that these B and C would come from application of finite number of elementary row and column operations on A. Let us prove this theorem. From the definition of rank, it follows that rank of a matrix has to be less than or equal to m and n both, and therefore R can be at most minimum of m and n. So if R is 0, that is the rank of the matrix is 0, then A is nothing but the 0 matrix, and then D has to be equal to A. Suppose that R is not 0, then A cannot be the 0 matrix, and now we prove this theorem by induction on the number of rows of the matrix, that is M. So let us start with M is equal to 1, that means the matrix A has only one row and n columns. Then by suitable elementary column operations on A, it can be put into the form where the first entry, that is the 1 1 entry, is 1 and rest all 0. And then you see that this is the desired form D. In this case rank is 1, therefore the top left corner would have identity matrix of size 1, that is just the number 1, and then the 0 matrix, and therefore the statement is proved. for m is equal to 1. Let m be bigger than 1. Let Aij be a non-zero entry at the ijth position of the matrix A. Then by a number of elementary row and column operations, we can bring this non-zero entry at the top left corner, that is the 1/1th position, and then again by suitable operations we can make all other entries of the first row and the first column 0 and make the 1/1th entry 1, which means that A takes this form where the 1/1th entry is 1, all other entries in first row are 0, all other entries in the first column are 0, and then there is a matrix A dash which is an m minus 1 cross n minus 1 matrix. Therefore, A dash has m minus 1 rows, and we can apply the induction hypothesis on A dash to get that desired form, the form D, and then it gives us the required form D for the matrix A. This proves the theorem. Now, the first corollary, which says that if A is an m cross n matrix over a field F, then rank of A transposed is the same as rank of A, and rank of A is the same as the row rank of A, which is the same as the column rank of A. So, what is row rank of A? It is the dimension of the subspace spanned by the m rows of the matrix A in the vector space Fn, and column rank of A denotes the dimension of the subspace spanned by the n columns of the matrix A in the vector space Fm. Well, this is an immediate consequence of the previous theorem, where we proved that after some elementary row and column operations, A can be put in that form D, where the top left corner has a block which is the identity matrix and rest all 0, and if we apply that, then this corollary follows immediately. We will see another corollary of that theorem. So, let us start with an n cross n matrix over a field F. In as usual denotes the n cross n identity matrix over F. Now, consider the augmented matrix A bar In, which is nothing but the matrix A on the left hand side, and then there is an augmentation by the n cross n identity matrix. So, the augmented matrix has exactly n rows and 2n columns. If we multiply the augmented matrix by A inverse from the left, then we get the new augmented matrix, which is A inverse A bar A inverse In, but A inverse A is the identity matrix In, so it is the augmented matrix In bar A inverse. So, we see that the matrix A inverse indeed comes as the right hand part of the augmented matrix, and that can be obtained by multiplying the augmented matrix AIN by the matrix A inverse. Let us understand the corollary first. Every invertible matrix is a product of elementary matrices. So, suppose A is an invertible n cross n matrix, then we know that rank of A has to be n, and by the previous theorem we know that there are invertible matrices B and C such that BAC is the matrix D, which is nothing but the n cross n identity matrix in this case, because rank of A is n. Therefore, D is B inverse C inverse, and B inverse C inverse are both products of elementary matrices. Therefore, we have proved that every invertible matrix is a product of elementary matrices. So, let us write A inverse as product of elementary matrices, EP, EP minus 1 and so on up to E1. Therefore, we can write EP, EP minus 1 and so on E1 multiplied by the augmented matrix AIN, and we know that this product is nothing but the augmented matrix IN A inverse. We know that multiplication by elementary matrices from the left amount to application of elementary row operations. Therefore, what we have proved is that if we start with the augmented matrix AIN and apply suitable elementary row operations on this augmented matrix, then it can be put into the form IN A inverse. This gives another method to compute the inverse of the matrix A. Let us now revisit system of linear equations, and we will see that we can talk about solvability of a system of linear equations using rank of the matrix. The theorem says that if A is an m cross n matrix over a field F, then the homogeneous system of equations Ax equal to 0 has a solution space which is nothing but the kernel of the linear transformation LA. Let us recall that the definition of LA is nothing but LAX is AX. Therefore, X is a solution if and only if X is 0, if and only if X belongs to kernel of LA. And we know by the rank nullity theorem that the dimension of kernel of LA, which is the nullity of the linear transformation LA, is nothing but n minus rank of A. Therefore, the solution space of the homogeneous system of equations has dimension n minus rank of A, and if rank of A is strictly less than n, then n minus rank of A is positive, and therefore the homogeneous system of equations has at least one non-trivial solution. And the second part of the theorem says that if Ax equal to b is a non-homogeneous system of linear equations, then the system has a solution if and only if rank of the matrix A is the same as rank of the augmented matrix AB. Therefore, if we can compute these ranks of the matrices A and the augmented matrix AB, then we indeed have criteria for solvability of system of linear equations, both homogeneous and non-homogeneous. This theorem talks about the uniqueness of the row reduced echelon form of a matrix. So, let A be an m cross n matrix of rank R, where R is positive. Suppose that B is a row reduced echelon form of A, then the number of non-zero rows of B is R. For each I from 1 to R, there is a column Bji of B such that Bji is Ei, that is the canonical basis vector with 1 at the ith position and rest all 0. The columns of A numbered J1, J2, Jr are linearly independent. For each k in between 1 and n, if the kth column of B is D1 E1 plus D2 E2 and so on plus DR ER, then the kth column of A is D1 AJ1 plus D2 AJ2 plus dot 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 DR AJR. Now, these 4 parts of the statement actually imply that the row reduced echelon form has to be unique. Why? Because rank is of course a well defined number, and based on rank R, the columns where the standard basis vectors appear are also uniquely determined. And therefore, one cannot have more than one choice for the echelon form, given that the echelon form has a particular wedge shaped structure where the zeros and ones appear according to a rule which we have seen before. Rank of a matrix is indeed computable, and it can be computed through the row reduced echelon form. In fact, the number of non-zero rows in the row reduced echelon form of a matrix is the rank of the matrix. And we have seen that the row reduced echelon form is indeed unique. Therefore, if we have to answer questions like solvability of a system of linear equations, homogeneous or non-homogeneous, then it makes sense that we start with the coefficient matrix or the augmented matrix and start applying elementary row operations, reduce it to its row reduced echelon form, and then we know what the rank is and apply that theorem which talks about existence of solution in terms of rank of the matrices.